Welcome back to All for C Learning session 41. In previous session we learned that iodoform reaction, acid medium, base medium mechanism, rate with respect to chlorine, bromine, iodine, and why polyalpha halonization do not take place in presence of acid medium. That all we learned. I hope that you got conclusion. Base catalyzed iodoform word is wrong. Base promoted iodoform, because base is getting consumed in the reaction. So base catalyzed is wrong. Correct word is base promoted. If you observe the mechanism, it is very clear. OH minus abstracts proton and converts into H2O. So base is getting consumed. That's what we have to say. Base promoted mechanism, but not base catalyzed. But in acid medium alpha halonization, acid catalyzed but not acid promoted. Okay, base promoted mechanism, acid catalyzed mechanism, alpha halonization reactions. Now let us see how iodoform differs from chloroform and bromoform. In the beginning of previous session we learned that chloroform and bromoform are colorless liquids, whereas iodoform yellow crystalline solid, and whose melting point is 392 Kelvin, means 99 degrees Celsius, 99 only, minus 273 means 119 degrees Celsius, and it has a pungent odor, and it is soluble in organic solvents like alcohol, carbon tetrachloride, there only, but insoluble in water. As per like dissolves like principle, here it is non-polar, preferably soluble in non-polar solvents or organic solvents. And this compound iodoform is steam volatile. You should remember that steam volatile compounds. Which compounds are steam volatile? So in previous session we learned that orthonitrophenol, orthohydroxybenzaldehyde, salicylaldehyde, they are all steam volatile. So this compound also belongs to same category. It is a steam volatile. Chloroform upon reaction with silver nitrate. There is no reaction. Let us see. CHCl3 plus AgNO3. If it is pure, in case of that silver nitrate, no precipitate, means no reaction. So if any reaction happens, this Ag plus has to take that Cl minus, and you are getting AgCl precipitate. So this one already we learned in the chemical properties of chloroform, as in CHCl3, Cl minus does not exist. Because it is non-polar. That's why I do not give pure chloroform, do not give any white precipitate with silver nitrate. White precipitate of what? AgCl. So pure chloroform do not give white precipitate of AgCl with silver nitrate. If it is impure, then in such a case, means chloroform is going to convert into carbonyl chloride or phosgene. Along with the phosgene, HCl formation takes place. We learned that, right? CHCl3 upon photochemical oxidation that takes place. Photochemical means in presence of sunlight. We are getting COCl2 and HCl. So impure chloroform means which undergoes oxidation in presence of sunlight. That chloroform can give white precipitate of AgCl with AgNO3. That is because of HCl, presence of HCl, right? So there HCl is there, not because of COCl2, not because of CHCl3. Hope you got the point. When we are adding silver nitrate to chloroform, we are not getting any precipitate, white precipitate of AgCl, because of Cl minus does not exist in CHCl3. But iodoform can give. I am repeating, iodoform can give. Means CHI3 with silver nitrate, we are getting yellow precipitate of AgI. Sir, in case of CHCl3 you mentioned that won't happen, whereas in case of CHI3 you are saying that AgI precipitate formation takes place. How, sir? Because there in CCl, that is less polar and bond length is short. In case of Ci, more polar and bond length is long. In other words, Ci bond energy is less, whereas CCl bond energy is more. That's why with silver nitrate, iodoform can give AgI white precipitate, whereas with CHCl3 do not give any white precipitate of AgCl, whereas CHI3 can give yellow precipitate of AgI. So this one in general we are using as test for chloroform. Test for chloroform and iodoform means to distinguish which one is chloroform and which one is iodoform. Of course, based on the color we can identify, but whether it is iodoform or not, that we can notice with silver nitrate. With silver nitrate, AgI precipitate you are getting. And one more thing, here Tollens reagent, with Tollens reagent, this is nothing but extraordinary case. Tollens reagent is also ammonical silver nitrate, means ammonia solution is there, NH4OH will be there. So let us assume CHCl3 undergoes hydrolysis, base hydrolysis, you are getting formate, right? Formic acid salt formate, which upon acidification you are getting HCOOH, right? But remember, HCOOH also has a terminal of aldehyde. From one end it looks like aldehyde and in another end it looks like formic acid, right? So because of it has acid phase also, it can respond Tollens reagent. I am repeating once again, don't get confused here. Silver nitrate reaction can be given by iodoform. This is clear. But the same reaction cannot perform by chloroform. That point completed. Now second point what I am saying, this haloform upon hydrolysis, base hydrolysis, then you are getting formic acid salt, right? Formic acid salt upon acidification you are getting formic acid. Formic acid can respond to Tollens test. You remember this point, you may get question, means in order to distinguish iodoform and some other one, right? So don't get confused in between these 2 points. Next one, iodoform is less stable compared to chloroform. Iodoform is less stable compared to chloroform. Iodoform it itself undergoes oxidation in presence of heat. It gives carbon monoxide, iodine and water. Iodoform is less stable compared to chloroform, and iodoform undergoes decomposition. Iodoform in presence of oxygen and heat, it converts into carbon monoxide, iodine and water. So here iodine, liberation of iodine is important. Because of CHI3 has a tendency to liberate iodine, this one is used as antiseptic property, and in antiseptic property here it liberates because of iodine, not because of CHI3 itself. CHI3 itself it is not antiseptic. Because of CHI3 upon oxidation it liberates iodine. Because of liberation of iodine it shows that antiseptic property. So it is very clear, iodoform generally we are using as antiseptic. Why? Because it is unstable, it readily undergoes dissociation. Upon decomposition you are getting iodine, that's why. Tincture iodine, yeah, we know that, tincture iodine. So this one only. So CHI3 in general dissolved in alcohol, and which upon long standing or when we are shaking that you are getting iodine. Iodine has antiseptic property but not CHI3, and it is less stable. Let us come to test for iodoform. With silver nitrate, iodoform gives yellow precipitate of AgI, and we know that chloroform or haloform gives which one? Carbylamine reaction. Carbylamine reaction already will end. Now, which type of substances can give haloform reaction? Haloform reaction given by ethyl alcohol. In primary alcohol family, only ethyl alcohol. Except ethyl alcohol, no other alcohol can give. Why? Let us see. I am going to consider propyl alcohol, which consists 3 carbons. N-propyl alcohol or N-propyl alcohol, which consists 3 carbons. Now this one, because of halogen in first step acts as oxidizing agent, this one upon oxidation what we are getting? Propanol. So with respect to this carbon, alpha carbon is this one. This alpha carbon now consists how many hydrogens? 2 only. But in order to get iodoform, how many hydrogens required? It must and should possess 3 alpha hydrogens. Right now we do not have 3 alpha hydrogens. That's why we do not give iodoform reaction. Sir, next carbon possess na? Next carbon, beta carbon containing hydrogens are not acidic, and beta carbon containing hydrogens are not substituted by halogens. That means beta halogenation do not takes place. Only alpha halogenation takes place. Here we need alpha hydrogens. That alpha hydrogens only we are having 2. That's why there is no haloform reaction except ethyl alcohol. Any other primary alcohol family, any other alcohol do not give. This one is fixed. Second one, ethyl chloride can give na sir? Yes, ethyl chloride can give, because ethyl chloride it itself cannot give, but ethyl chloride undergoes SN1 reaction, SN2 reaction, and it converts into ethyl alcohol. If you convert this ethyl alcohol, if starting compound is ethyl alcohol, which upon SN2 reaction, nucleophilic substitution reaction, if Cl displaced by OH, in such a case you are getting ethyl alcohol. Ethyl alcohol can be oxidized to acetaldehyde. Acetaldehyde can perform iodoform reaction. This is clear? Acetaldehyde, obviously either ethyl alcohol, ethyl chloride upon nucleophilic substitution reaction you are getting ethyl alcohol upon oxidation you are getting acetaldehyde. So all these 3 can perform reaction. So this one you can memorize as, in primary alcohol family only ethyl alcohol, in primary alcohol family only ethyl alcohol, which upon oxidation you are getting acetaldehyde. In aldehyde family only acetaldehyde again. In aldehyde family only acetaldehyde, except acetaldehyde, any other aldehyde. Let us see propanaldehyde, acetaldehyde. In aldehyde family first member is formaldehyde. It is not possible to give iodoform. No iodoform, no alpha carbon first of all. So formaldehyde do not give. Second member acetaldehyde. Acetaldehyde can perform iodoform reaction, right? Now 3 carbon containing aldehyde, if you consider what happened. 3 carbon containing aldehyde is propanaldehyde. As just now we discussed that alpha carbon possesses only 2 hydrogens. Absence of 3 hydrogens at alpha carbon, it do not give any haloform reaction. That's clear. Next one, 2 halo. Methyl group must here. Methyl group must here 1 alkyl group. Other alkyl group whatever it may be. That's your wish. 1 alkyl group must be methyl. Okay. And if second carbon attached to Cl, again this one upon nucleophilic substitution reactions what happen? You are getting alcohol. Right? So this one upon nucleophilic substitution reaction you are getting alcohol, means 2 chloroalkanes. You can say what do you have to say? 2 chloroalkanes. Here in 2 chloroalkanes first carbon is methyl, it remains as such, and the remaining alkyl group whatever it may be and whatever the number of carbon atoms are present, that's not criteria here. 2 chloroalkanes these are. 2 chloroalkanes upon SN reactions you are converting into 2 alkanols. 2 alkanols upon oxidation you are getting methyl ketones. So here C double bond O group attached to methyl. Other alkyl group whatever it may be, it can perform iodoform reaction because of, with respect to this C double bond O, this carbon is alpha carbon. So obviously alpha carbon consists 3 hydrogens. Because of presence of 3 hydrogens, it can perform haloform reaction. 2 amino alkanes also, just like 2 haloalkanes, 2 amino alkanes. Sir, how can we replace that NH2 group, sir? Of course, we cannot replace that NH2 group because NH2 minus is obtained from very weak acid ammonia. Ammonia actually has basic nature. From that, if you subtract, if you remove proton, NH2 minus. So NH3 conjugate is NH2 minus. So it is a strong base. Being strong base, strong nucleophile. Being strong nucleophile, it cannot be displaced easily, no doubt in that one. So NH2 group cannot be displaced as such as NH2 minus. Instead of that, we need to do a small, we need to perform a small reaction. That is this one upon diazotization followed by water. Diazotization, what happened? This one is a primary amine or secondary amine? This one is a primary amine, secondary amine. Oh, obviously, sir, why you are asking like that? We know very well, because of nitrogen attached to carbon. This carbon is attached to 2 alkyl groups. Obviously, this carbon is secondary. That's why amine also secondary. Amines primary, secondary is independent of the carbon which NH2 is attached. I am repeating. Amines primary, secondary, tertiary is not depending upon to which carbon is attached? It depends upon nitrogen contains how many alkyl groups. In such a case, nitrogen is attached to only one alkyl group. That's why it is primary amines. We already learned that diazotization reaction, primary aryl amines or primary aliphatic amines undergoes diazotization. This NH2 converts into N2 plus. That N2 plus is good leaving group. Then upon treatment with water, you are again getting alcohol. You got the point here. As NH2 group, we cannot displace directly. For that, what we have to do? We need to do diazotization. During diazotization, what happened? NH2 converts into N2 plus. So NH2 converts into N2 plus, and that N2 plus has to depart. And upon treatment with water, you are getting alcohol again. 2-alkanol. The 2-alkanol upon oxidation, we are getting ketone. And lactic acid alpha hydroxy carboxylic acid. Of course, with respect to this one upon oxidation, you are converting into C double bond O. With respect to this C double bond O, this carbon is alpha carbon, and alpha carbon again consists 3 hydrogens. That means lactic acid can perform iodoform reaction. Lactic acid can perform iodoform reaction. Lactic acid upon oxidation, we are getting pyruvic acid. That pyruvic acid is nothing but alpha keto propanoic acid. So alpha keto, and with respect to this one again alpha, and this alpha carbon is attached to 3 hydrogens. So this one can perform iodoform reaction. And methyl ketones, one must be methyl, another one any alkyl group. It need not be any alkyl group, any aryl group also. Methyl phenyl ketone, also called acetophenone, because of presence of alpha carbon containing 3 hydrogens. This one can perform. So far we learned that which compounds can perform. Now let us focus on the compounds which cannot perform but looks like same, but which are having same environment but not going to perform iodoform reaction. Let us see. So let us see this example. CH3 C double bond O, CH3 is acetone, in which one of the alpha hydrogen is replaced by acyl group C double bond O, CH3, acetyl acetone. This one, if you observe here, with respect to this C double bond O, this carbon is alpha. With respect to this C double bond O, this carbon also alpha. But have a look here. What about this carbon? This carbon again alpha with respect to either of these two C double bond O group. Now, from beginning onwards, we are discussing that alpha carbon containing hydrogens are acidic because of C double bond O group is electron withdrawing group. Fine. With respect to this CH3, one C double bond O group attached. For this CH3, one C double bond O group attached. Whereas for this CH2, 2 C double bond O groups, means there are 2 electron withdrawing groups are there. Since the presence of 2 electron withdrawing groups for this CH2 group means methylene group, whereas for this methyl and this methyl, for both the methyl groups only 1 C double bond O, we can say these methyl hydrogens are less activated compared to methylene hydrogens. Methyl hydrogens are less activated compared to methylene hydrogens. In such a case, this one upon reaction with I2 and NaOH, can we say iodoform reaction? No. What happened here? CH3, C double bond O, CI2 here, C double bond O, CH3. You are getting this product. Since only 2 alpha hydrogens, that 2 alpha hydrogens get replaced by 2 iodine, and you are getting this product. From this product, you are not getting any, you don't have any possibility to get iodoform reaction. That means here case 1, when you need to, even though alpha hydrogens 3 are there, you need to verify whether that alpha hydrogens are more activated or not, or compared to that alpha hydrogens, if any other hydrogens are more activated, you need to check out that. Let us consider one more example. Here CH3 C double bond O. You only mentioned sir, methyl ketones can perform iodoform reaction. CH3 group, C double bond O group, methyl group is there, C double bond O group is there, and this one is say OR or OC2H5, OCH3, whatever it may be. These are nothing but ester. Let us consider this one is OC2H5. Its name is ethyl acetate. Not only ethyl acetate, any acetate ester group, whether it perform iodoform reaction or not. Can it give iodoform reaction or not? Check out here. this one upon reaction with the base and I2. So since with respect to these three, this C double bond O group, this carbon only alpha carbon, there is no other carbon like earlier example. So only one alpha carbon that also consists of 3 hydrogens, means it satisfies the condition. Fine. Upon halogenation, this one converts into Ci3, C double bond O, C2H5. Until here, fine, that's clear. Now after that, what we are expecting? OH minus has to come and attack upon this C double bond O, right? So if it happens, Ci3, CO minus and OH, OC2H5 we are getting. After that, what happened? Upon reversal of this charge, what we are expecting, the Ci3 has to come out as Ci3 minus. But instead of that, what happened, you know? Upon reversal of this charge, OC2H5 has to come out. It will come out instead of this Ci3. Then the product what we are getting here is Ci3, C double bond O, OH plus C2H5 O minus. See here what happened. Did you get iodoform? Let us see the mechanism once again. This is nothing but ethyl acetate, ethyl ethanoate also. And this ethyl acetate or ethyl ethanoate consists only one alpha carbon, not like earlier example. This one consists 3 alpha carbons. And here this alpha carbon also consists 3 hydrogens, which satisfies condition which required for iodoform. Now this one upon base and I2, we are expecting triiodination, Ci3, C double bond O, C2H5. After formation of this one, OH minus acts as a nucleophile. This OH minus has to come and attack upon this C double bond O, pi electrons are shifted back. And upon reversal of the negative charge, Ci3 we are expecting, but we are getting OC2H5 minus. So instead of Ci3, OC2H5 minus we are getting. So what do you say? Is it possible to get any? Is it possible to get any iodoform reaction? No way. So esters do not perform this reaction. Esters do not perform this reaction. Have a look here. CH3, C double bond O, OC6H5. This one is a phenyl acetate or phenyl ethanoate. So check out what happened. Is it possible to get iodoform from this phenyl acetate or phenyl ethanoate or not? So try to write the mechanism. Now CH3, C double bond O, CH2, C double bond O, OC2H5. CH3, C double bond O. If you consider this one as substituent, this is ethyl acetate. Ethyl acetate. In ethyl acetate, alpha hydrogen replaced by acyl group. So in this case, C double bond O, just similar to first example. And this C double bond O attached to this alpha carbon consists 3 hydrogens. Whereas this C double bond O do not attach to any alpha carbon here, but with respect to both C double bond O, this carbon only alpha. Means here there are 2 alpha carbons. This alpha carbon activated by alpha carbon containing hydrogens activated by 1 C double bond O. Whereas this alpha carbon containing hydrogens activated by 2 C double bond O groups. Now what you expecting product here? OH minus and I2 base in presence of base. How this reaction proceeds? So generally what you say? This alpha carbon containing hydrogens only 2 are there. This one do not perform iodoform reaction. Check out the mechanism whether you are getting or not. Now similar to this one, here 1,3 cyclohexane dione. 1,3 cyclohexane dione. What is your answer? Is it possible to give any iodoform reaction or not? What is your answer? Sir, C double bond O group. With respect to C double bond O group, this carbon is alpha, this carbon is alpha. Here both the alpha carbon consists only 2 hydrogens. Here also 2 hydrogens. Similar to this C double bond O also, this one is alpha and this one is alpha. Both the alpha carbon consists only 2 hydrogens. Sir, this one do not fulfill basic requirement, that is alpha carbon must and should attach to 3 alpha hydrogens. 3 hydrogens must. That criteria not satisfied here. So obviously what do you say? This one is not going to perform or not going to give any iodoform reaction. Okay, fine. Let us see the mechanism. So any compound, instead of looking the compound whether it gives iodoform reaction or not, better to go for mechanism here whether really it do not give iodoform reaction or it can give iodoform reaction. Have a look here. If we are using base and I2, here simple, which alpha hydrogens are more activated? No doubt these 2 alpha hydrogens are more activated because of these 2 alpha hydrogens are activated by 2 C double bond O groups. That's why we can say this one is more activated. Now we can say double bond O, here iodine, diiodo. Again, if you want to see complete mechanism, in first case we are getting carbanion. This carbanion is resonantly stabilized. Resonantly stabilized. Now it acquires carbon-carbon double bond character. Upon this one, addition of I2, then what happened? We will get double bond O, monoiodination and double bond O. Still it consists one more hydrogen. Repeat with OH minus. Again it abstracts hydrogen. That carbanion is more stable because of presence of iodine. This negative charge is more stable because of iodine along with their 2 C double bond O groups. This one also resonance structure. This one also involves in resonance like O minus. This one upon reaction with I2 we are getting double bond O, I double bond O. So far both the alpha hydrogens which are activated by 2 C double bond O groups are substituted by 2 iodine. Now this one upon reaction with base, this OH minus has to come and attack upon carbonyl carbon, either this C double bond O or this C double bond O. Then we are getting O minus and OH. Upon reversal of this charge, these electrons get back. Then we are getting here double bond O, here Ci2 minus. This bond is going, this ring will be open and it exists as C double bond O OH. Now proton transfer because of it is acid and Ci2 minus this one. Further OH minus and I2 with respect to this one alpha carbon. Of course this one also alpha carbon. This alpha carbon containing hydrogen is activated by only one C double bond O. This one activated by along with C double bond O 2 iodine atoms also. Then we are getting Ci3, C double bond O minus. This one upon attacking of base has to come and attack upon this C double bond O. Because of this one here positive charge is more compared to this one. Here this carboxylic carbon do not bear any positive charge. Now O minus, OH, Ci3, C double bond O minus. Upon reversal of this negative charge, what happened? Ci3 has to come out as Ci3 minus. Ci3 minus plus what you are getting? C double bond O, OH, 2 methylene groups, CH2, CH2, C double bond O minus. Later, this Ci3 minus abstracts proton from carboxylic acid and it converts into CHI3. So, we got iodoform reaction. Initially, what do you think? This one cannot perform any iodoform reaction. No iodoform reaction because basic condition not satisfied. No one alpha carbon bears 3 hydrogens. But even though 1, 3 cyclohexane dione can perform iodoform reaction. So any substance, whether it is going to give iodoform reaction or not, that we need to verify as per mechanism. Check out one more example here. CH3 C double bond O, here para-nitro acetophenone. Para-nitro acetophenone. Can it give iodoform reaction or not? Check out itself yourself.